So, hello everyone, my name is Ozun, and today I'm going to be talking to you about managing side effects with Swift. So, what side effects are we talking about? Is it, the back pain from sitting too much in front of the computer, or the elevated heart rate from drinking too much coffee? And while those are very important to manage, we are going to talk about side effects in our code. So, I will talk about why we should care about side effects and managing them in a minute. But first, let's get on the same page about the definitions, like what side effects, what exactly we mean by side effects. And to do so, let's take a look at two kinds of functions that are important in the context of this talk. And these are pure functions and effectful functions, or functions with side effects. So let's take a look at pure functions first. So pure functions, here we have a couple of examples. We have a multiply that just multiplies two numbers, and a critical damage function that takes a base damage and multiplies it by the multiplier of 2. So why are these functions pure? The definition is actually really, really simple. Pure functions don't depend on or mutate any external state. They may depend on input arguments or on local variables defined within bodies of these functions. They may also depend on other pure functions like this multiply function in critical damage. And that's pretty much it. That's the whole definition. These are the rules. But these rules enable some interesting properties for pure functions. These include so-called referential transparency, which means for the same input, pure functions always produce same output. And this means that they are deterministic and predictable. So this is very powerful, and you'll see in a minute why. Now, pure functions enable equational reasoning. What this means? So take a look at these two versions of the same program, where we create a tuple of two numbers by multiplying 2 by 2 twice, or in the second version, we kind of do it once and then use the same output twice. So are these the same functions? Are these the same programs? Can we say that they are the same? Yeah, they are the same. And we can confidently say that they are the same without looking anywhere outside these few lines, anywhere in the code base. We don't need to see any other state. And this means local reasoning. So we can reason about these two programs locally. And this is very powerful because we can perform these kind of refactorings, these kind of substitutions with high confidence. Now, pure functions are really easy and fun to test. We don't need to have any complicated test setup. We just provide inputs and check the outputs. Mm-hmm. It's just not sleep. OK, we're good. Now, pure functions are idempotent and retriable. This means that we can call the same function multiple times and don't worry about resetting some state or cleaning up some resources between calls. This can be very useful when we do something like retrying failed network requests. Pure functions can be cached or memorized. We can calculate the output once, cache it, and then retrieve the value for the same input from the cache without needing to call the function. And this is very powerful for various optimization techniques. And finally, pure functions can be parallelized. Because they don't depend on anything other than inputs, we don't need to synchronize any mutual shared state between multiple pure functions. So we can call them even on separate computers and then calculate results. Now let's, in contrast, look at the effectful functions. So in contrast, effectful functions do depend on or mutate external state. So for example, we can make our multiply function effectful by mutating some external history state that logs the history of events. Maybe we're building some sort of calculator UI app which benefits from this kind of side effect. Now, can we now tell that these two programs are the same? What do you think? Are they the same? No, no, correct. They're not the same anymore. Because the first one records history, 2 operations into the history, and the second one only does so once. And depending on our requirements, one of these programs is correct and the other one is incorrect. So what this means is that we can no longer apply local and equation and reasoning. We need to understand what the external state holds. And this means that performing these kinds of refactoring becomes quite dangerous, so we are kind of walking on a minefield here. Now, otherwise pure functions like this damage function can get effectful if they call into other effectful functions, so they kind of get infected by them. They also non-deterministic. For example, maybe we introduce like a bonus component to our critical damage, which retrieves value from user defaults. And what this means is we can no longer predict the output of this function call. That is because somebody somewhere can change user defaults, which often refers to a spooky action at a distance. So other examples of side effects include any sort of disk I/O, working with files, user defaults, databases, any networking, any sort of randomness, dates, UUIDs, etc., any sort of concurrency and threading, and any interaction with I/O, like showing values on display, using camera, microphones, etc. Now, to sum up, pure functions are deterministic, reusable, composable. We can reason about them locally using equational reason, very easy to test. Effectful are non-deterministic, often unwieldy, hard to reason about, and hard to test. So based on these kind of properties, it might sound like pure functions are just amazing and effectful are kind of silly and stupid. But that cannot be further from truth. Because pure functions, by definition, having these restrictions, they are restrictive and limited in how we can use them. Whereas effectful functions are incredibly powerful and immensely useful. Because in the end of the day, what we want from our programs is some sort of side effects like making network requests and writing data to databases. So the goal of today's talk then, to explore, is it possible to have kind of the best of both worlds, where we can write programs that are deterministic, composable, easy to test, yet are very powerful and useful. So we will explore, today, due to time constraints, we will explore only 2 approaches to side effect controls, and there are many, many more. One approach would be very, very familiar to most of you. And the other one would be radically different. So I thought it would be an interesting kind of comparison. So we're gonna look at the simple number guessing game that we built for console. It asks you to make a guess of a number from 1 to 5, then expects you to provide input in the console, tells you if it was correct or not, asks if you want to play again. We can say yes, make another guess. Here we are correct. And if we say we don't want to continue, the program terminates. So it's a very simple game. Now here's the implementation, like in traditional sort of naive implementation. We print instruction to the console, we generate random number, and wait for users to provide input into the console. Then we run some logic where we compare if their guess was correct or not, and give them the answer. And we print the result to the console, ask them if they want to play again, and again wait for their decision. And finally, we map their input decision to true or false, whether or not they want to continue. And we say that there's a bit of flexibility. They can say and or no or 0, which means no. Any other input means they want to continue. And we wrap everything in a while loop, which kind of runs the program indefinitely until it terminates. So a very simple program. I hope everybody on the same page, right, what we're doing here. For simplicity, we're just going to focus on a single kind of game loop which finishes with whether or not they want to play again. OK, so let's look at this program from the standpoint of the program definition and the way the program is called somewhere like in a main function. So we care about a few things here. We're talking about side effects. So the first question is, how are effects declared in this program? Implicitly or explicitly. So if we look at the function definition here, at the signature of the function, there's nothing in the call side that indicates that any side effects are being performed. So anything can be happening in this function. So we say that the effects are declared implicitly. Next question is, who controls the implementation of these effects? And the answer here is the program. So like the program goes and uses int random, readline, etc. And finally, who controls the execution of these effects? Again, it is the program itself, the callee. So the program decides when to call these side effects. So keep these questions in mind. We'll come back to them a few times during this talk. So the first approach is incredibly simple. I just call it divide and conquer, not a scientific name. But the idea is the following. If you look at any program whatsoever, it usually is a combination of some logic, some pure business logic, and some side effects that the program performs. And usually these are kind of interleaved and mixed together one by one. So the idea is to identify these pieces of a program and separate them. So let's do that for our program. So first we have 3 lines of code which obviously perform side effects, like we're reading and writing from console and we're generating random numbers. Then there's a block of pure logic which maps a guess to the correct or incorrect answer. Then again goes a block of side effects, read and write into console, and again a block of logic that maps their decision to true or false. This is clear so far, right? Now what we do is we can split this up and extract these pure business logic functions into separate functions. Now these functions now take the arguments that they need to operate, and now that we have these functions separately, what we can do is we can go and test them easily, having this like low friction input-output tests that allow us to exhaustively fully provide a full test coverage for these functions. Now, if we go back to our program, now we use these extracted functions. So what we've achieved here might seem like something very simple, yet it is quite remarkable because we've been able to test the core functionality of our app in an exhaustive way without needing to use any other more advanced techniques. So even if you walk out from this talk and the only thing that you kind of take from it is, hey, let's learn how to identify pieces of pure logic in our program and extract and test it, that would be wonderful already. Now, of course, we ideally want to test our whole program. So far, our program still mixes effects and logic. This means that there's really no way to test it in any way other than actually like running the program and manually verifying it, maybe some sort of advanced end-to-end tests, but we cannot unit test it. So to nobody's surprise, the next thing we're going to look at is dependency injection. So I'm sure all of you are familiar with dependency injection in one shape or another. And what I want to say is that dependency injection, as the name implies, cares about dependencies. But really what dependencies mean are implicit side effects. So it's more like side effect injection here. So we have 3 kind of representations of 3 side effects we have here, console and random. Again, there's many ways to implement dependency injection. We don't really care about specifics. We care about concepts here. So I'm going to go with like the most traditional kind of book, a textbook example, which uses interfaces or protocols to provide an abstraction over the implementation of the effects. So we have a random number generator protocol and a console for print and read line. And so we can use these interfaces and replace calls to side effects with calls to this interface. So now we have this indirection that allows us to control these side effects. And of course, we provide like a live implementation that calls into actual side effects we used before. So now going back to our diagram with caller and program, now that we have dependency injection in place, let's look at our question. So how are effects declared? And I say almost explicitly, because now if you look at the function signature, it now features kind of random number generator and console, which allows us to make like an educated guess that most likely the program needs these dependencies to perform side effect. It might not be necessarily true, but most likely it is true. So I almost explicitly declaring effects here. Now, who controls effect implementation? Now it's the caller. So the caller now decides how does print into console or random number generation is implemented. So you probably heard of this term inversion of control, which is very impressive during the interview. And really what this means is we have inverted the control over effect implementation from the program to the caller. So this is what it means. Now, of course, let's go back to our tests. We wanted to test our program. So again, to no one's surprise, we can create a couple of mocks, one for random number generation, which uses a fixed number, and the other one for console that keeps track of printed messages for further inspection, and the other one which reads line from a fixed input. So our test might look something like this, where we create a couple of mocks, we fix random number to be 3, and then we decide that for inputs, we first input like 3, and then we answer no to the question, do we want to continue? We run our program, and we inspect that printed messages match what we expect here, and the play again is false because we said we don't want to continue. So fantastic. Again, like nothing groundbreaking here. But here's the thing. What if we went here and swapped places of read line to be the first thing, the first side effect that performs, and only then printing the instruction? So what the result would be is, here's our game. Now our game starts with just like expecting the input, and user doesn't know what to do. There's no instruction. So essentially, our game is completely unusable, even though it is functionally still correct. So like we can still input 1, and if it's a correct guess, well, the program will tell it's a correct guess. But still, the program is completely unusable. So this represents a critical bug in our program. Yet our test will not catch this, because all we look at is like the total output of the console. This is because this test does not validate that the order of effects. It doesn't validate that first we gave an instruction and then we waited for the input. And of course, we could go and improve our mocks to keep track of order of execution of functions. But make no mistake, doing so would be incredibly hard. And most likely, you won't do this by hand. You will reach out for and pull in some sophisticated mocking framework, such as Mockingbird, that allows to do so. So what I'm trying to tell here is that using mocks to test programs can get complicated pretty fast. And so here's a handy diagram that I conveniently nicked from my former colleague Matt's talk called Test Doubles Are a Scam. I highly recommend this talk. So what this diagram shows is, here we have a number of unit tests and the difficulty of writing them. So when we are testing pure logic, like we had with those extracted functions, we tend to have many incredibly simple input-output tests. And we can get full test coverage. When we test effects, we tend to have a small number of complicated end-to-end integration tests. But if we try to kind of test our programs which mix these two, we kind of get worst of both worlds, where we have, if we want to have any sort of exhaustibility or any sort of test coverage, we will have to be forced to write large number of quite complicated tests. And speaking from my professional experience of working on a team of over the 50 iOS engineers, I can tell you that if there's any friction in writing tests, people tend to just skip them, right? So they tend to cut corners, such as, well, we just won't test the order of operations, even though it represents the critical bug. So here's a question. Can we make testing of programs easy, fun, and mockless? And I specifically say mockless, which refers to any test doubles, because it kind of is a common source of friction. So this is where the second approach comes in. Now, this is going to be quite radical, and there will be a bit of code, but don't worry about looking into details of code. Try to get the concept, and I try to make the best effort to show you the concept. So here's what we have with dependency injection. We inject side effect implementation from the caller into the program. So what if we did something opposite, where our program doesn't care about side effects at all? All it does is it describes side effects or effects it wants to perform and returns it to the caller. And then the caller maps these descriptions to actual side effects. So here's how it looks like in the code. Again, comparing to dependency injection. So here we have a simple greet function that just prints hello name. And we inject the implementation of peer function using the function argument. So here we have the call side, which injects the implementation of print into the program. Now, the effect descriptor approach, we can describe this effect using a simple struct, which has a text that needs to be printed. And then our program simply returns this effect that describes what needs to be printed. And then the call side calls our function, gets this description of the print effect, and actually calls the effect. So this is interesting, because now our program can be completely isolated from any notion of side effect implementation. And this is very powerful for modularization. This is what my team uses. It is very powerful. So let's see how this concept can be actually expanded to like actual proper programs. So we have our effect implementation. Ideally, we want to have some sort of effect handler or effect executor or interpreter, however you call it, which is basically a class or a type that encapsulates the side effect implementation. Now, we can describe other effects in a similar fashion. So we can have like read line, it doesn't take any arguments. Random number takes the range as an argument. And we could have like multiple functions that take the corresponding effect and maps it to actual side effect implementation. But what we really want is we want to unify these effects under a single type, and enum with associated values is a perfect fit for this. Now, of course, enum cases already provide discriminators for different effects, so we don't really need those separate types. We can just inline the arguments here. Of course, more complicated effect descriptors, such as a HTTP effect, might still benefit from having a separate type to kind of encapsulate all the arguments here. Now, with enum, we can have a single perform function that switches or maps over the type of effect descriptors and calls into specific side effect implementation. Now, your next question should be, OK, but what am I supposed to do with the outputs that side effects produce? And more importantly, how can I write actual useful programs this way? And this is where I need to introduce you to two styles of programming. One is called direct style of programming, which is simply we have like a double function that takes a number and returns it double, and we can call multiple times in a row and then print it. The other representation is called continuation passing style. So here we have the same double function, but it doesn't return anything. But it takes kind of like a completion handler or like a continuation that takes the return. So then the same program would look like this. Again, it kind of looks like a completion handler in a sort. So these two programs are equivalent. Indeed, any direct type program can be automatically converted into continuation passing style. So continuation passing style is often used by compilers as an intermediate representation of programs to perform various optimization and analysis, because it allows to have total control over the execution of next step of a program. But why do we care about this? This is because when we describe effects as enums, we cannot just simply state which values these effects return like we would with normal function. But what we can do is we can supply continuation as an associated value. And so, ideally, what we want is we want each continuation to continue to the next effect. So we have this kind of recursive effect type, which continues from one effect to the next, to the next, to the next, and so on. So we can write, here's a simple program, echo program, that simply reads your input and prints your output back to you. And it does so recursively, so read line, print line, et cetera, et cetera. So the same program using like the normal imperative instruction would look like this. So we read line, print line, and then recursively repeat. But what we have on the left is a pure description of a program. It does nothing. It describes how the program should work. Whereas what we have here is the set of execution instructions, which means executing side effects, which means we cannot test it in any way other than manually, etc. So OK, let's carry on. We can simplify this code slightly a bit by providing a type alias for continuation to avoid kind of the function types here. Makes it a bit cleaner. The read line continues with string, print continues with void. Now, with that in place, we can now perform our effect. And now, for example, read line has a continuation. So we call actual read line side effect. We wait for the user input. We get their input string. And we pass it to the continuation, which takes string. And it, in turn, produces the next effect, which we recursively call. So what this means is when we have like a echo program, it's a description of a program, and we feed it into the effect handler to be performed, it goes and actually performs these side effects in actual console and does so. But OK, let's make it a bit more interesting. So we want some logic as well, right? So for example, we want to have a logic that if the input is exit, we finish the program. Otherwise, we carry on echoing back. So
exit in a program is also an observable effect, right? Like when you run a program and it terminates, you do see this happening. So it's a legit effect. But it doesn't have any continuation, which means that, well, the program doesn't continue from that. Which means, simple implementation, we just return. So like we interrupt recursion. OK, wonderful. So let's go back to our number guessing game and finish its implementation. So we're missing one more effect, which is random number. So again, it takes the range for the random number, and it continues with the generated random number. Implementation is very simple. Call into int random and continue with random number. And, but our program, when it finishes, it tells, do we want to play again or not? So we add like a play again Boolean. And since our program finishes with a Boolean, the perform function now returns the Boolean. So when we actually create our description of our program and feed it into the handler, it runs the whole program until the completion and then gives you the play again Boolean. OK, so before we continue, one last thing. Since we're working with enums, and enums are kind of, they have this problem of extracting associated values using like switch or guard case-led syntax. So we can create like a quick helper accessors that just simply pull out the associated values if the case is correct. So they all are kind of Boolean, optional this way. This will come in handy when we start testing our program, so we don't need to do this like super ugly guard case-led syntax, and instead we can simply say, hey, if the effect is print, give me its text and continuation, or fail the test. And we don't need to write this by hand, but it's incredibly simple. It's just like syntactic sugar. You can create like a macro that does so, or you can use one library called case passes that does this for you. Anyway, this is just syntax. Don't worry about the kind of complexity of it. So this is how a program looks like in this style. It looks pretty much the same way as our initial program. You can see the nesting happening here, which is the continuation passing style. But the logic itself, like the mapping of answers, it's all the same. So you can still read it top to bottom pretty much the same way. Now let's step through the test of this program, which is the most interesting part of this approach, in my opinion. I will like follow the outlines. They will kind of like imagine we are debugging the program. We're stepping through the debugger. So when we create the description of our program, we start in like this is the whole program, right? Next, in our test, we verify that the first observable effect that happens is printing. And we get the text and continuation. We validate that the text is what we expect. And then we call continuation, which continues the program to the next step, which is, in this case, random number generation. So we check that the next step is random number. We validate the range. And then this is very interesting. So we directly feed the input argument for the random number. So in this case, we pass the value of 3. So the program continues with number 3 as a secret number. Next step is read line. And we get the handle on the continuation, and we directly feed it input 3. So we carry on. The next step, the program runs the logic. So because numbers match, we go into correct case, and we continue to print. And so we validate that the output is correct. We continue further. Next step is, again, printing. Again, we validate that it's giving us the instruction. We, again, continue to the next step. We check its read line, and we directly feed it the answer no. And because it's the answer no, we fall into the exit with play again false. So what we see here is a very kind of straightforward and powerful way of testing our programs, going just step by step in exactly the same way the manual tester would do when they would test the program in the console. And in this test, we do verify that indeed the instruction came before we asked for their guess, which was the critical bug we represented. We introduced a few slides before. And more importantly, there's no mocking. So yes, this test has more lines of code, but this test does not require any prior setup. We don't need to kind of carefully tailor, think about our mocks, think about like what should be the fixed number. We just simply go, okay, you want my read line, here's number 3 for you. So I find it very, very powerful. Now, but how do we test effect handlers, like the actual mappings of effect descriptors to side effects? And the answer, we test them using proper integration or end-to-end or UI tests. We don't need to unit test this because we managed to unit test our program completely without even needing any sort of notion of side effects. So going back to our diagram, what we can have is we can test logic with effect descriptors easily with like having large number of like very simple, very like straightforward input-output tests. Okay, but let's address this guy, the elephant in the room. So we kind of started with something on the left, which was like a direct style imperative procedural step-by-step code. And we finished with this continuation passing style, which has this like nesting going on. And I think we can all agree that like this nesting looks nice, nesty. It's not great. It's not very pleasant to look at. But what if I told you that it is possible to bridge between these two worlds? I already told you that we can convert any direct style program to continuation passing automatically. And like, it's kind of trust me bro thing, but like really, there's a Wikipedia article, there's like huge body of research on this. It's everywhere. So here's an interesting thing which probably most of you know. Now, Swift concurrency addressed exactly this thing where we used to write continuation passing style asynchronous code where we used to have like completion handlers for any sort of operations. And Swift concurrency came in and like, hey, use await, but then you can write direct style code, which is fantastic. I love it. I want all my code to be direct style code. Now, but you also may know that we can bridge between these two worlds. And Apple provides this thing, check continuation, which allows you to kind of bridge between these two functions. And what this means is that we can go and define our effects using this enum kind of DSL with continuations, and we can bridge it into a normal kind of dependency protocol with like normal function calls that asynchronously return values. And this can be all auto-generated by using macros. So if we had these like dependencies like this, we could take our normal procedural code and update it with minimal changes. Now, of course, every call into like dependency that produces side effect needs to be asynchronous. But I think it's quite reasonable, actually, because, well, first of all, most of side effects are asynchronous, but also because await doesn't necessarily mean stop and wait. It's just a potential suspension point. So if our random number is actually synchronous, there will be little to no delay. And so what this means also is that we can actually write normal direct style procedural code like this, which would be bridged into this kind of continuation passing style under the hood, sort of. And finally, what this means as a final consequence is that we can write code like this, which otherwise would require complicated mocking or like dependency injection or some sort, but we can write tests like this, where we can simply step through the program step by step from one observable effect to the next and feed in inputs as we please. So yes, final slide. So let's recap. Now, we started with a very simple and familiar techniques such as divide and conquer and dependency injection. So again, I'm gonna say, if you walk out from this talk, the only thing you take is, hey, next time I want to extract some piece of code, let me use not some subjective or arbitrary metric like my function shouldn't be more than 3 lines of code, or my function should do one thing, who knows what this one thing is. But now you can look, hey, does this piece of code perform side effects, or is it pure logic? If it's pure logic, we can extract it, completely test it, and if you stop there, you're already gaining huge benefits. Next, if you use the dependency injection, keep on using it. It's a decent, legit way to control side effects, but be ready to bear a weight of kind of added complexity of using mocks, test doubles, etc. So maybe you would need to cut corners here and there. Maybe you would need to throw out some test cases that are too complicated to test, but that might be exactly what you want. Finally, if you feel convinced that you want to step up your side effect management game, you can explore various topics. And I'll share like links for you as well. So today we looked at effect descriptors, which really is sort of a DSL and interpreter pattern, where we had the DSL describing the program and interpreter running the program. There are other things. There are things like monads, which I like to call effect containers, which is a completely different approach to side effect management, but you can read up on this. There's a thing called tagless final, which is even more obscure and mystical, but again, you can read up on this stuff and explore. There are concepts known as functional core imperative shell, which is more like splitting, more like a bigger way of architecting your programs. You can read up on that. Finally, you can go and explore architectures such as Redux, the composable architecture, the Elm architecture. All of them use some sort of effect management technique. Redux and composable uses monads and dependency injection. The Elm architecture uses effect descriptors that we use today, and that's what my team uses. So feel free to connect to me. I don't know if we have time for questions, but I have a website called Swiftology where I write about similar stuff. And actually, the upcoming article will be on this exact topic, managing side effects, but where I will explore all the techniques I know. So everything, not only what we discussed today. So yeah, feel free to connect. And yeah, you can shoot me questions or find me in a breakout rooms. Thank you. Thank you very much.